energy equation. Okay. Now, and we are asked to analyze a steam turbine. Okay. So we have a steam turbine. Now you recall that for a steady flow system, an open system, the number one assumption is that the mass flow through the system is constant. Okay, so that means m dot in is always equal to m dot out. Okay, so that being said, as a review, let's say we have for this and the steam again. Now you recall that we are stepping through air, steam, air, steam. Now that is majorly because most engineering thermodynamic systems that produce work and power are usually based on these two fluids. Okay, so that's why we usually refer to air and steam. So say steam turbine. So now we have the properties of the steam turbine at this point as 2 megapascal for let's say 500 degrees C and so on. Of course, we also giving velocity of inlet, let's say 50 meters per second, and okay. So let's say we have this as our input, and let's say the Z, the height of let's say 10 meters, and then here we have properties at, let's use 15. Why don't we use okay, let's use 15 kilopascal, and the velocity of the outlet is equal to 100 meters per second, and the height, the Z from the datum, let's assume is 6 meters. Okay, and then we have to find the various quantities in the steady flow. Okay, so the first thing I want you to recall is that the steady flow energy equation is given by the following formula, which is m dot into h1 plus v1 square over 2 plus gz1 plus q equal to w out plus m dot h2 plus v2 square over 2 plus gz2. Okay. So recall that that's our steady flow equation. So now the first thing we have to get is our h at this point, at the inlet, and our h at the outlet. How do we do that? Now to get the h at the outlet, and let's also say we are giving the entropy at the outlet to be, say, 7.5 kilograms, kilojoules per kilogram Kelvin. Okay, good. Now, what we want to do here is to first say, okay, at this point, like we usually do, what is the state of steam at this point? Obviously, I know it's going to be superheated because the saturation temperature at 2 megapascal is lower than 500 degrees C. So this steam is superheated. So I'll go to my superheated steam table and obtain my H1. So how would I do that? So 20 megapascal for 2 megapascal, which is 20 bar, we'll have this value, and I'm looking under 500. Okay, so under 520 megapascal, and that's 3467. Okay, 3467 right here. So I'll take that value, 3467, H1, 3467 kilojoules per kilogram. Remember, units are very important in any engineering problem. Now, the next thing I want to do is to calculate my H2. Okay, so how am I going to get H2? Remember, I have two properties already, this property and this property. So these two properties fixes the state of steam. Okay, so let's decide. First of all, we want to determine, is our steam at the outlet superheated or wet vapor? Okay, so to find that out, we need to go to our steam table and check for this relation I'm going to write. It states that if the S at this point, S is greater than, is less than Sg at that pressure, which is 15 kilopascal, then this steam is what? Wet steam. That shouldn't be a worry, because we remember our curve of our saturation dome for steam. You remember that at this point, this is saturated liquid, this is saturated vapor, this is superheat, and this is wet. So of course, if the S of wet, if this S, right, is less than the saturation vapor value, that's the Sg, you know saturation vapor properties are represented with G. So if this S is less than Sg, that simply means it's inside the wet region. Okay, so let's come back to how we can pick that up. So now I'll go to my steam table and check Sg at 15 kilopascal. Now, the first thing I want to make sure you understand is you have to convert it from 15 kPa to 15 bar. So from 15 kPa, 15 kPa is equal to 15 times 1000 pascal. And to convert to bar, I will divide by 10 to the power 5. So if I do this thing, we'll have 0.15 bars. So I've now put it in bar. Okay, so let's back to the table. Of course, I'll go to my saturated water and steam and look for 0.15. So right here we have 0.15. Okay, it's in between these two points, right? And then I can now come here and check my Sg property from 0.15 is, of course, is between 0.8, is between 8.0 and 7.9. Obviously, those two values, I don't need to interpolate. I already know that 8.0 and 7.9 is greater, either of those values. Okay, if you notice, we're reading between 0.112 and 0.14, right, and 0.16. Of course, 1.5 lies between these two values. Okay, so whatever value is here, for 0.14, we have the value of 8.031, and 0.16, we have a value of 7.985. Now, of course, you know 0.15 is going to lie between these two values, is it not? Now, whatever the value here, it cannot be lesser than 7.9. So let's just assume the value here is just the value. Let's just assume, because we are saying it's between 8 and 7.9. But step through to this part, we can see that the value that we are given as S is 7.5. Okay, and you can see that 7.5 is very less than 7.9. Okay, so that means that the S is less than the Sg. And if S is less than Sg, what does that tell us? It tells us that that steam is wet. So we'll come here and then clean up this. Okay, and then we write state. This state is wet steam. Now this will mean I need to obtain my X value at this point. Okay, so X is equal to the entropy S minus SF over SFG, or the more traditional formula you know, which is S equal to SF plus X S.F.E.E. So these are the two formulas. Now I'll step back to my table, and of course we know the S, we need the SF and SFG, right? So now that's the interpolation we wanted to jump earlier, and now we cannot escape it now, but I'm going to show you how you can get the value of 0.15 at those 2 points, okay? So follow me as we draw our table and obtain that value. Alright, so right now we are going to have 0.14, 0.15, 0.16. And 0.14, the S at that point is 0.737, and 0.772. So we're looking for SF at this point, and also we're also looking for SFG. So, and those 2 points are 7.294 and 7.213 SFG. Okay. So right now we'll step to our calculator to give us those values. Okay. Oh, but there's a trick I should show you. Okay. Now you can see that 0.15 is the average of these two. So all I need to do is add this divided by 2, add this divided by 2. So if I want to do that, I will have SF to be equal to the sum 0.737 plus 0.772 divided by 2, and that is 0.7545, and SFG is equal to 7.294 plus 7.213 divided by 2, and that's 7.2535. So now we've obtained our SF and SFG. We can now write X will be equal to 0.7545, 7.5, which was given the question, minus 0.7545 divided by 7.2535, and X will be equal to, if I type that out, we have 7.5 minus 0.7545 divided by 7.2535, and that is 0.92996, approximately 0.93 Dryness fraction. So now we have the dryness fraction, so our H2 will be equal to HF plus X HFG. Oh, so we can also obtain F value and G value. All we need to do is to go back and select our 2 points and then put the values right here for F, HFG, and HF. So we would have, at the end of the day, we would have the HF at, okay, let's just obtain it from the table. HF is 220, 232. Okay, so let me just write this somewhere. 220, 232, and 2376 and 2369. H. Okay, so these are the two values I have to get the average. I'm just trying to obtain the value of HF and HFB as 0.15 bar. Okay, so if I do that, I'll have 220 plus 232 divided by 2, and that is HF is 226 plus 0.93 into HFG, 2376 plus 2369 divided by 2, and that is 2372.5. So everything becomes our H2, and that will be equal to so our H2 is have been obtained from the calculator 2432.425 kilojoules per kilogram. So this is our H2, and that's all you need to know to analyze circles that you are giving entropy instead of the X dryness fraction. The rest thing is, as we discussed in our previous video, where we talked about the steam circle and we analyzed the various velocities of inlet and Z. Okay, so from that, from the velocity, you can get the kinetic energy, which is v2 squared minus v1 squared divided by 2, and then the potential energy, which is gz2 minus gz1. Okay, so once you have those other two terms, you plug gz1, gz2, v1 squared, v2 squared, and then you have your h value. Now notice that since it's a turbine, the q through it is 0, because adiabatics have assumed that no heat is flowing, so this term tends to 0. So all you have to do is to get the individual quantities and subtract. Okay, so that's very simple to analyze steady flow devices.